Hello everybody. It is time once again for another customizing normals video where we talk for like 30 hours about not normals. Now at this point I understand if you think that the title of this series is false advertising. The first few videos were about normals, but we've been talking about geometry nodes ever since. But that is all about to come to an end. This video is the last things we need to know to build the setup that we need to really get into normals math. Also, it's really cool stuff. We have two main topics. First, we're going to be deep diving into transferring position in geometry nodes and looking at a few of the cool things it'll let us do. Geometry nodes has opened up a whole new frontier of like rigging and modeling and getting things into position that has barely been touched. Blender's rigging tools aren't bad when it comes to armatures, bones, constraints, and all that stuff. But there's so many things that we end up bone rigging that we really just want to snap to surfaces and attach to them. We do have a couple modifiers that let us do that, but they're a bit finicky to work with. So we're going to learn some better methods as kind of a collateral damage of building this wider setup. Where we're going with all this is a setup that I call the normals canvas, which is what we use to put together our shapes in the end. We've got our head, we have a UV unwrap of our head as a reference, and then we can do things like, here is a decal that is being positioned over that UV unwrap and is being projected onto the face wherever we put it based on those UVs. And since it's UV based, this actually will respond to any deformations we make on the mesh. It's kind of terrifying, but you know, should be used to that by now. This method can support pretty much any shape, like here's a monkey. And the size of the shape doesn't really matter. Just being wrapped on. And pointy shapes. So any instance of where you want to get a shape onto something else and you want to work with it flat, this just makes your life simple. Maybe that seems a bit weird, but how about something practical like retopology? Just work with your topology flat, overlaid over the old topology. Anything you do is just getting wrapped to the object. I think this actually exists in some other programs. Neat. And we'll finally get to one of the things from my overview video. This plane is being wrapped onto this face via the UV map, like a texture, to create this. And then the normals are being transferred from it. So as we change the resolution of the plane, it picks up more of the face's details. Or we can be subdividing this afterwards, or smoothing it, or whatever. So this is a great method to take an existing shape and reduce detail, smooth it, clean it up, but just the normals. And since it's UV based, it just follows the forms. We don't need to worry about rigging it or anything. And of course, we're doing tons of noding all the way through, building on what we've learned before and also adding more. I'll be adding all this to the project files on Gumroad, of course. And don't forget to like and subscribe and that you can support me on Patreon. The setup we're going to be making uses a lot of position transferring. We've done some before to close gaps between things, but there are even more uses for it. We're going to look at a bunch of the common uses using a simple setup before we try them on the real face, because that's a lot more complicated. Let's start with the most basic possible. We have a torus, we have a plane. The torus has these geometry nodes on it, with the plane as a target object being brought in here. And we are simply transferring the position of that plane to the torus with nearest face interpolated, set position, and it has snapped it to the plane. This is basically Shrinkwrap. So exactly what this has done is, for each vertex of the torus, it has found the nearest point on the plane, and gotten its position, its interpolated position, and it has overridden whatever position that vertex was in with this new transfer position. It has set it to that. So what happens now if the plane deforms? I've got some simple deforms to bend it. Well, things are looking a bit messy now, and that's because this is just transferring from the deformed to the original position. So now, for each vertex, it's coming in, finding the nearest point on the now deformed mesh. So this is basically still just Shrinkwrap. And it doesn't really work with deforms. It's shrink-wrapping to the deform, but now there's a big space between them, and that's causing problems, and it's all gribbly. Let's turn that off and drop down to our next setup. So this looks similar, but this time we are using the offset input on set position instead of position. What that means is, before we were setting to a position, now we are modifying the current position by some amount. And that amount is the transferred position minus the position attribute. So here, the position attribute for the transfer, this is getting the position of the geometry it's being evaluated for. So this will be the position of the plane, whereas here, this gets evaluated here, so this is the position of the torus. So we are offsetting by the difference between the transferred position and the original position, which gives us the exact same thing as setting to the original position. So why am I showing you this if it's exactly the same? Well, actually, it was for this that I unplugged, which is that we are now back at the original shape. So we've transferred the position, and actually we moved this geometry, but then we restored the original position with an offset. So I wanted to introduce that idea. Now, of course, if we bend our plane, this still doesn't hold up very well. In fact, it's an even bigger mess now because we are offsetting by the difference between the deformed and the original. So we have all the same problems with this being deformed. So we've got some things here that are sort of working and other things that are not. Let's look at another little example here. So this is, once again, the same thing, right? Except we've got more nodes to do the same thing. What's going on here? So this time, before we do the set position, we are capturing the position of the original geometry. We are separating x, y, z, and we are subtracting the y from 0. So what's that actually giving us? That's giving us the distance each vertex is from 0, which is the plane in this case, but that's a coincidence. It could be something else. I mean, the plane isn't necessarily there. 0 is going to be in the same place. So this has given us the offset of each vertex on y. So we're setting the geometry to the plane, and then we're offsetting on y. Only the y difference. So this has only restored the y, but it's identical to the previous example where we offset by all three axes. And that's because there's only a difference on y. Because when we do this set position, it's only moving it on the y-axis. It's moving the points straight inward. And that's because we're using nearest face interpolated. So it's just finding the nearest point, which will just be on the y-axis. Now we will see a difference as soon as we bring our bend deformations back. So here, it's like all inside. Like if we turn that off, everything is getting bumped inside. Whereas on this one, it's kind of bumping it back out evenly. It's wherever this point is, it's moving either down y negatively or positively, depending on its previous distance down y. So this is obviously much better. The problem is, it's moving only on y. So it's kind of like we've shrink-wrapped it onto this curved surface and then re-expanded it. Whereas what we would really like in the end is for it to follow the deform as it's happening, so to speak, and then have its shape restored. Then this would actually be wrapped to the surface of the deform. And that behavior I just described is actually what the surface deform modifier does. I'll target the plane, I'll bind it, it's now bound to its current position. Then, as you deform the plane, it wraps with it. And it retains some of its original shape. It's a bit messy, though. And it's distorted because the surface it's on is distorted. But yeah, basically, surface deform, that's some nice functionality to have. But the problem with it is you need to bind it, which means if this geometry changes at all, like if it gets subsurfed, then the surface deform breaks. And to get around that, you have to like duplicate it and bind another one to the subsurf version, and you have to rebind it anytime you change the mesh. So it would be great if we had that functionality without dealing with the bind. And that's what we're going to get. Moving on to the next examples. So we've got the same torus, we have the same deformed plane, and we have a copy of it that I'm leaving undeformed. And I've made it wireframe so we don't get confused. So this time we are bringing in our undeformed and deformed version of the same object. So there's our undeformed. I'm going to hide that. So I've hidden it, but we're looking at it within the geometry nodes. There's the deformed. We transfer the position from the deformed to the undeformed and capture it. And then we get the difference between the deformed position and the undeformed position. And then we transfer that to our torus. And when we set that, it's wrapped onto it. But it has not lost its thickness. It wasn't flattened. And more importantly, it is deforming with the target. So if we set both of these to 0, and then scrub them on, we can see it getting the bend. Which, it doesn't necessarily look good, but, that's a different matter. And I've got a surface deform here that we can compare it with, and it is still a bit different. It's sticking in the same way, but the surface deform is handling the volume in a better way. And that is because the surface deform is taking the normals of the target into account. So we'll need to fix that, but this method is working, transferring just the offset of the deformed and undeformed, and transferring from the undeformed position, so there's no problems with things lining up. But we do have to have 2 copies of the object, which is kind of annoying. But in this next version, we're getting the same result, but we don't need 2 copies. The reason for this is this geometry nodes group up here on the deformed mesh. If I turn it off, then things get crazy. What is this doing? Well, it's extremely simple, actually. It is outputting the base position before the deformations take place. It's saving the undeformed position. So in these nodes, what we're looking at here is we bring in the deformed, we capture the deformed position, we bring in the base position that was saved on it, and we set it back to its undeformed position. Then we get the difference between deformed and undeformed and do the same transfer of the offset. So basically, we take the deformed mesh, we restore its original position so it's undeformed, and that's how we have it in both the deformed and the undeformed state. So essentially, our saved position is taking the place of the bind we need for surface deform. But unlike the bind, it doesn't have all the problems of you needing to rebind when anything changes, because you are dynamically saving all the time. So if we make a change to the mesh, that's technically happening before any of the modifier stack. So we're just saving whatever state the mesh is in. So this is super convenient. Also, it can even survive if we do things like subsurf. Because when you subsurf a mesh with attributes on it, it is automatically applying those attributes to the subsurf version. It subsurfs the attributes too. The new geometry inherits the attributes appropriate to its location. So yeah, this is surface deform without all the problems, and it's just fantastic. And while we're looking at it, this is a good time to mention a new feature. You may have noticed that I have switched to Blender 3.2 since the last video, because that's come out. So now we have access to some new nodes. We have store named attribute, and we have also input named attribute. Well, it's just named attribute under input. So what does store named attribute do? Well, it does the same thing as if instead of plugging into this node, we outputted it, and in the output selected an attribute. So we're already used to doing that, but it lets us not have to do that. We don't have to make a group output, which is nice, and we don't have to set something in the output field for it to get used. So basically, this is adding the convenience of being able to always store on the same attribute. Like, if I wanted to make a group that always writes to that attribute, then this lets me do that, and it saves clicks. Also, it lets us input our attribute based purely on a string. So here, I've set this to be position base, and this isn't like an attribute selection field. This is just a text field. Of course, it doesn't like it if I actually do that. But wait, there's more. Also, in our group settings, over here, we can set defaults for it. So the default is this text string. So anytime we make this as a group, it's going to have that. So yeah, we can set defaults as well. Actually, you can set defaults for all attributes now, not just text strings. I think that's also new, but if it was in 3.1, I missed it and I didn't talk about it before. Then also we have the named attribute node. So this writes to an attribute and this retrieves an attribute. And this writing and reading is happening in the order the graph executes. So notice if I disable this and then I go here, that position base attribute doesn't exist. And then if I enable it, it does. So yeah, I could do that, and right now I'm setting it to its same position, but if I disable this, then I'm setting it to 0 because there's no longer an attribute. Which is actually another thing you should know about. This position base attribute that I'm writing to does not actually exist in the attributes list for this mesh at all. And this is something else that I think is new in 3.2, but I'm not really sure because I never tried before outputting to an attribute that didn't exist on the mesh. You could always type whatever you wanted in an attribute output. But either way, this is useful. You don't have to go and manually create an attribute to write to and read from it. If you're storing an attribute, if it exists on the mesh here, it will store in it. And if not, it still exists. It's still being stored. If we go to other places, then we can still access it. And it's just not showing up here. So it's an invisible attribute or something. And we know that because, here we are using that position base on this inputted target deformed, and it's working just fine. So yeah, basically that's some new nodes and some information that is either new or, more relevant with those nodes. But that makes it a lot easier to keep things organized. Okay, next example, getting complicated now. So here is where we have finally matched up with what our surface deform was doing. Well, almost matched up. Actually, ours is a little nicer. So what are we looking at here? There's a lot more nodes than before. We're still doing the same thing as above, where we're getting the offset of the deformed and undeformed and transferring it. But this time, we are transferring our torus flattened. So we get our torus, we capture the position, we flatten the torus on Y, and then before setting that position, we're transferring from a flat mesh to a flat mesh, so there's not going to be any transfer distortion. We set the flat torus to the deformed surface by setting the offset, just like the previous setup. And then here, we are restoring its volume, but this time it's being restored properly. You may remember from the previous example that we had the problem we were trying to restore the volume, but it was only being restored on Y. This time it's being restored with the normals taken into account. It's restoring what used to be the Y thickness, but now in the normal direction. So let's take a look at how that's being done. What we have here is a displacement group, and this works the same as the good old displace modifier that you've probably used. What displace does, well, there's several modes on the modifier, but the regular mode is normal. You add displacement in the direction of the normals of the mesh. And that's what's happening here. Let's take a look at how this group actually works. The core of it is we're taking the position and we are adding actually the normal back here, and we are setting a new position to be the old position plus the normal, which makes a giant mess. Now this might cause you to think that this means it's not working correctly, but actually if we turn that off and we just put on a regular displace modifier, it's also a mess. So this is just a mess because it's too large of a displace effect. Whereas if we turn that down, then it's doing the right thing. I mean, it's a mess because it's moving in the normal direction, but the normals are kind of crunched by being stuck onto the face of this thing. So yeah, strength of 1 means it is being moved 1 blender unit, which is why that's just way too much. So we scale that down on the modifier, or in our group, we scale it down with this scale node. So let's plug that in instead. If we're just doing normal to scale, then at scale of 1, if I turn the group on, it's that same mess. And at 001, now we have the same thing that the modifier was giving us. And you might happen to remember the length of normals, vector length, is 1. So we're adding 1 in some direction to position, which is why the default value, the default amount it scales out is 1. So yeah, it's literally just vector math that we're already familiar with. So everything else in this group is just some controls to augment that. For example, instead of just using the base normal, this is a switch where if nothing is plugged into override normal, then it uses the base normal because it's checking for any length on the inputted value. And if something is inputted, like a transfer normal from another mesh, then it will use that normal instead. So that's just an input check like we've seen a lot of times before. Then down here, we have the inputs for strength and factor. So the strength is how much to scale, and that is a value that is multiplying 1, because the input amount is 1. Then this scale vector math node is actually just a multiply node. It's called scale because it's multiplying a vector by a float, but we could get the exact same results if we take a multiply node and just plug that in. It's the same thing. Exactly the same. So this is just a useful UI feature. Scaling is multiplication. So the core of the scale math down here is actually strength times factor. And the reason these are different is the strength is setting how much to displace by, and then the factor is just for us to turn it on and off or reduce the amount. And this is because the strength will often be not a value that we enter for the whole thing. It's not a manual value. It'll come from some offset. It'll be a different value per vertex, that sort of thing. So we don't technically need fac in like this use case, but it's just a nice thing to have. And we also have this switch for if we use the actual strength or the strength's absolute value. Now, this is a bit confusing. What this does in practice is makes the back of our mesh disappear. Well, actually, it's not going anywhere. It's just been displaced in the same direction, and so it's doubled up. And that's because this mesh is symmetrical, or at least, before we wrapped it on, it was. So why do we have this if it just messes things up? Well, it messes things up or not, depending on what our normals are like. So right now, this is being displaced on the normals of the torus when it's flat like this. So this face in the front is pointing this way, which is kind of like a negative y. And this face in the back looks like it might be the same face, but it's actually not. It's, this was a mesh with volume that has now been flattened onto itself. So this is pointing that way. So if we displace with a positive strength value right now, it's just going to be displacing along whatever direction the normals are pointing on. So it doesn't matter if we use absolute value or not, because this is just a positive number. But what happens if our strength is negative? Well, turn off absolute. Now we'll make that a negative number. And now it's hard to see what's happened, but it's actually displaced through itself. It's just hard to tell because it was flat. So maybe I should duplicate this. So we've displaced positive, and now we will displace negative, and we've re-achieved flatness, except, we moved the other way on the same direction, and now it's chunked itself even more. But yeah, so a negative strength will move you in the opposite direction than the normal is facing. So the issue is that our strength input can contain both positive and negatives on different vertices. So let's remind ourselves, we started with our torus, we saved its position, then we flattened it on Y, then we wrapped it. So since we saved the position back here, and we bring that over here, and we're getting the difference on Y. So for each vertex, we know how far away from the y-axis, from 0 on y it is. For this middle loop, it's going to be 0. For these vertices, it's going to be minus some value, and for these, it's going to be plus some value. And in this case, I'm doing a subtract from 0. Actually, before I had this set on a multiply of -1, which is going to give us the same thing when its location is mostly 0, but could be different if this mesh was not near 0. So it is better to use subtract there. So this strength value, this offset distance that we're going to use, is negative for some vertices and positive for others. So that's why when we just plug it in, currently on the normals that were pointing this way, if it was a positive direction, then the vertices moved that way. But if it was a negative amount, then on normals pointing that way, it would have moved things in the opposite direction of the normal. So basically, we need all of our values to be positive when we're dealing with a mesh that already has thickness and has normals pointing in different directions. So that's why we have absolute. Now we're going to transfer normals from the deformed mesh, which is basically a sphere. And that gives us a slightly cleaner result because it's going to respect the curvature a bit better. It's not a huge difference, like if we do this, and it's not a huge improvement just because this is a fairly low poly shape going to a fairly low poly shape. But if this is a more complex surface, if these were both a lot more complicated, this could matter quite a lot. So if you need to do this or not depends on what your shape is and on how mangled your geometry has gotten from being stuck on it. So what we can see now that we're using the transfer normal is that it's all displacing in the same direction again. So now we need it to not be absolute. And now it's working. So the reason for this is before, this normal was pointing that way and this normal was pointing that way. But now they've been transfer normals from just one surface that doesn't have any depth. So what's happening now is that all of the normals are pointing in the same direction, which will be whichever way they were pointing before. And remember, in geometry nodes, there is no concept of a back face. Well, on the mesh level, there is no concept of the back face. So what we're doing now is telling it to actually use the positive and negative of the strength value. Some faces are going to be displaced positively along the normal, and some are going to go negatively along the normal. So yeah, a deceptively complicated thing that you would have never run into with the regular diffuse modifier because you couldn't give it a custom normal. Well, you could transfer normals before it, but it doesn't displace on custom normals. It displaces on the actual normals. But in this case, we do have to worry about this distinction, and we can use it to our advantage as long as we build ourselves the controls for it. So to clarify what we're looking at here, this isn't quite analogous to surface deform because these setups assume we can get our source and destination flattened on each other to do the transfer. Our undeformed shape is flat, and we've manually flattened our object onto it. So if the goal is just to attach a mesh that has no volume and is already flat to a surface that it is flat on in the starting position, you don't need more than these nodes. But if you have volume like we do here, then they are going to distort the volume. So this setup is fixing the volume, but it is assuming we have these flat transform positions. So this is not quite an all-purpose tool for sticking a mesh to any other mesh in any position and then having it accurately follow through deformations and keep all its volume. We probably will get to those, but we don't need them for what we're going to be trying to do here because we will be working with flat shapes, because we're going to be working with UV unwrapped meshes. So let's get to our next example and take a look at those. At first glance, our third example looks the same as the second. But if I go into edit mode on the torus and I move it around, we can see that it is wrapping onto the target mesh, unless I go too far. And if I move it on Y, it goes crazy. And this is because it is actually being UV mapped on. This mesh is a reference for the UV map of this mesh. So wherever we put the torus in relation to this one is where it's going to be wrapped to the surface. And the reason it gets messed up on Y is because I didn't build the setup to deal with Y offsets, only to deal with X and Z. So this is the method that we'll be using with our face in order to wrap decals onto it to create the normal shapes that we want. So the setup is using 3 objects, but only one of them actually needs any geometry nodes. Our target, the deformed plane, just has its bends. This UV reference has geonodes on it, but it's not actually needed for the setup at all. I can delete it entirely and everything still works. It's just there as a visual reference so that when we're adjusting our torus, we can see what we're doing. So most of the work is actually going on the torus. But we're going to look at this first because understanding how it works is going to help us understand how the torus's nodes work. So first of all, our deformed plane has a UV map, which is very straightforward because it's just a plane. And our UV reference object is getting the deformed plane via its geometry node. If we turn these off, we can actually see that inside it's secretly a cone, but it doesn't use its own geometry at all in its node setup. The UV reference has 2 geometry nodes modifiers. I've done it as 2 separate modifiers. It could also be 2 node groups in the same geonodes graph. It doesn't really matter. The first one gets the target geometry, and it unwraps it and flattens it to its UV map, just like we were looking at the end of the previous video. Then the second one is taking that and transforming it into a different space and scaling it so that it's more convenient to work with artistically. Let's recap how the UV flattening works. Here we see the plane in UV space with 0 is the origin point, and then this is going up to 1. We can see it's 1 by 1, X and Y. So on the modifier, we're bringing in our target object, which is our bent plane, and its UV map. And it's just the default UV map called UV map that comes with primitives when you make them. And all you really need to do a UV flatten is you just need your geometry and the UV, and then you set the position, and that's it. The UV map is already a position per vertex in X and Y. There's no Z. So that's it. Now it's that in world space. So what's the rest of this group? Well, it's all things to make working with this a bit more convenient. I've been building up a bunch of convenient reusable groups. In this example, we're not even using a bunch of their features. Split edges and fix X centerline are both set to 0 here. But we're going to go over them now because we will be needing them up ahead. This object info group is a wrapper for the object info node, but making some of the features more convenient. So first we've got this relative switch. Inside the group, we have 2 copies of object info, one on original, one on relative, and a switch for which one we want. And that's good if you want to use the same nodes, say, for different setups, and some need relative and others don't, and you don't want to have to constantly copy things, because we can just make this an input on whatever group this gets used in. The bigger feature of this group is to check if there's incoming object geometry at all, and if there isn't, to use whatever geometry is plugged in here. So inside here, it is doing an input check. It is looking at the point count of whatever mesh is coming from the object input. If that equals 0, if there's no points inside, then it's going to return true, and it will use the inputted geometry instead. Otherwise, if there is geometry inside that object, then it will use that. So this is useful because you have many setups where sometimes you want to use something from geometry and sometimes you want to use an object. So this makes it easy to do that with the same overall node setup. Next, we have split edges. These are something that we sometimes need and sometimes don't. which is why we have a Boolean to control them. You may remember in the UV flatten example from the last video, we were flattening a face, and we needed to split the edges around that face, otherwise it created a big mess. So in this case, this lets us just split the whole mesh, or we could be feeding an attribute or a mask into the split edges if we wanted to split only part of it. And down here, we have our fixed position center line from the previous video, which again is a good thing to have if you have any disruptions in your UV map from UV transfer. In this example, we don't. So again, we have a switch and it's just not being used right now. Depending on where you use this sort of setup, we may end up linking up some of these inputs, but for this, we certainly don't need it yet. And then we also have a flatten Z, and that's for if you're using a position as a UV map that isn't actually a UV map, because then it may have some Z distance in it, some height. So this just chops that out. And I'm not sure if I should attach a switch to this. I put it in there, but I haven't actually needed it yet, so we may come back to this. So before we look at our second modifier here, let's take a look at what our torus is doing. It starts out in this position, which is the same as edit mode. And first, we have a save position like we learned about earlier. We'll need that later. Next, we have that same UV canvas transform that's on the UV reference. And when we turn that on, it flips the torus to match UV space, because we need it in UV space because that's where we're doing the transfer. We're essentially transferring between this mesh, unwrapped, and the torus in its UV space too, unwrapped. Next, it gets wrapped onto the target, and then finally the shape is restored, which is what the saved position is used for. So if you're not restoring the shape, you don't need that at all. So what exactly is this UV canvas thing I'm talking about here? So the problem we have is that UV space is 0 to 1, X and Y. I mean, you can go positive and negative, but that's the usual UV grid. So if we're going to use that as our intermediary position to transfer things through, we need to be able to get things into it. But it's kind of a pain to work with things in that space. And, we want a situation where we can be working with our mesh, like, in edit mode here. We want to work with our detail here and then have like our face or whatever over here and, move things here and see what they're doing here, which is what we end up with. Like, this is the behavior we want. So because of that, it is necessary to transform to and from UV space for artistic convenience. So that's what the UV canvas transform group is for. It has the ability to transfer things from UV space into some other defined space, or things that already match that space into UV space. And that's controlled by this reverse transform option. Let's take a look at exactly what it is doing. First of all, we start with the position and an input check if we want to override it. So by default, it has position as the position attribute. And what this input check is doing is simply checking to see if anything is coming in the base position field. And if it's not, then it just uses the default position. So same input check we've seen plenty of times. Next, we have some mapping going on. You may be familiar with the mapping node in shader nodes. Geometry nodes doesn't actually have that as a node of its own yet, but you can just make it as a node group, which is what I've done, and we'll look inside in a moment. For this first mapping node, the inputs are being set here in the node tree. So anything that uses this as a group or a modifier is going to get the same transforms. And that's kind of the whole point of this. We want to be able to transform whatever we want between UV space and our canvas space, which is 90-degree rotation and then scale to 0.2, scale down by 5. But just in case we need it for some reason, we have a second round of the mapping node, and this time it's with inputs going to the modifier or a group if we're using this as a node group. So that would be if you needed some change on some specific object that was different from all of this, like if things weren't lined up in global space correctly or whatever. And then finally, we have the option to set the position, and we also output the transform position. So we make the changes on the position value, but we don't necessarily set the geometry to it. And that's because this set position here is basically just a visual preview for us while working with it. When these are actually used later, it's just going to be using the transform position, which is actually a UV map if we look at the output. I'm setting that to a UV map, although it could be set to something else. And since this may be set to different things in different use cases, I've left it as a node group output and not used a stores attribute. The most important part of this group is actually this reverse option, because that allows it to play double duty and put things into UV space or out of it. So on our reference here, we are going from UV space to canvas, so it's not set to reverse. But on our torus, we're going from canvas space to UV, so it is set to reverse. And if we don't have it on reverse, then it's gotten these transforms again. It's left its original position and gotten rotated and scaled down to 1/5 size. Let's see how the group actually works. Mapping is actually pretty simple. There's not much here, and half of it is the reverse process. So the mapping is simply vector math. Add for location, the vector rotate node for rotation, and then multiply for scale. And if we want to go in the other direction, we divide to invert the scale, and we do that first. Then we go through the rotation, but with it inverted, and then we subtract, which would undo the same transform. So that's actually pretty simple. And I'm outputting it as both a position and as a face corner, because we might need this for multiple things. I'm not actually using that yet, but we'll probably use that in the future. So what do we need this second mapping node for? Our transform from UV to canvas space is global, but we also may need the ability to adjust an individual object depending on how it's set up compared to its own origin point. Notice that on our torus, the origin is down at the bottom left of the square, which matches this. When you do transforms, it all happens from the origin point unless you've defined them to happen from somewhere else. I've added a mix node here between the transformed and original position so that we can really see what's happening. As we scrub it, we can see that the meshes are doing their rotation, translation, and scale based on the origin point, which is 0 as far as that object is concerned. So what happens if the origin point isn't here? I've got a copy of the torus, which has its origin point set to be in its center. And if we turn that on, now we can see when it unwraps flat, it's unwrapped around its origin point, so it does not line up with where it should be in UV space. It should be over here, same as the other one. But it is not. The extra transform will let us fix this. So let's leave that in UV space so we can see what we're doing. And we can now give some translation to this in X and Y and get it into the right place. And I happen to know that the right values are 0.5 and 0.5, which doesn't look right, but it actually is right. You have to remember the origin point for this is over here, whereas the origin point for this is over here. So if we now line those up, it would be correct. In object space, it's in the right place. In global space, it's still offset, but that doesn't matter. It's also offset here, but again, that's because the origin point is higher. The other way you can think of this is that if we wanted these both to have their origin point in the same place, even as they are offset from each other, how much would the duplicate's origin have to move in order to be at the 3D cursor? And the answer is 0.5 divided by 5, or multiplied by 0.2. That's the same distance. So that might just be harder to visualize, but that's the basic idea there. So if you always work with your origin point in the same place, then you're not actually going to need this. But it's there for if there's some reason that you do have it in a different place. And there is a very good reason that that will come up, actually, which is if you're working on a mesh decal that you want to project onto your face, but you're using the mirror modifier, because then you need it to be have its origin point in the middle on X, and then it can't be down there on X. So that's why we have this to correct for mirrors mostly. Another quick note is that this transform group is not the only way to do a transform like this. We could do it on the object level, like take our object, rotate it 90 degrees, and then scale it down to 0.2, and we've done the same transform. And if we're only working with a couple of things, that can be easier than setting up all these nodes. But it's not quite that easy. It works fine for the UV reference, but if you're doing that kind of thing for the torus, where you want to work with it in edit mode, then we've got, actually, we need to do it the opposite. So minus 90 and then scale up by 5. Now it's in UV space, and then we'd apply this as the new base, and then we would undo that to put it back into the canvas space, and then we also have problems that geometry nodes isn't going to use the object transform necessarily, depending on how it's used and if things are relative or not. And, that would be fine on this torus, but it'll become a mess. And then also we have to do that sort of transform on every single object we want to work with this with. So the reason we use this node group, even though it does seem like kind of a hassle, is that it is less of a hassle in the long run once we get into complex setups. Okay, so what's next? We've got our torus in UV space, which matches that. And our next group wraps it onto the target. So we've got a new group, wrap mesh via UV, but it is made out of things that we are already familiar with. We've already worked with flatten to UV over here, and here it is again in a different context. Let's go through what we've got here. First of all, we are getting our target, which is our deformed sphere, and we are using that object input group that we talked about earlier, but this time we are taking advantage of the relative target feature. And that's because we want to be wrapping onto this wherever it happens to be without worrying about the UV space. Otherwise, it's going to think it's over here. And then, it's going to be in the wrong spot. So that's why that feature exists. Let's hide these other meshes so we can see just what we're working with here. So we get our target object, and that's coming in through the target override object input. And again, that's because this could be an object or it could be geometry, because we could be working with this as a modifier or as a group within another node tree. Then we capture the position. Then we set it to its UV position, exactly like our UV reference. That's literally the same thing. And we use that as the position to then transfer its previous position that we captured. And up here, we are getting our torus, and we have UV flatten again, and UV flatten actually contains that same object input group. So, and this might get a bit confusing, but the reason I didn't just put the object straight into the override on UV flatten is because I needed to capture its position first. Otherwise, this could have just gone straight in there. But, yeah. So we UV flatten our torus to its own UVs. It's UVs that were saved by the previous modifier after it had been transformed into UV space. And this is taking advantage of this flatten Z. So now our torus is flattened in UV space, and our target is flattened in UV space, and they are right on top of each other, which is perfect for transferring with nearest face. And we happen to be transferring the position of the target before we flattened it, but the same principle applies for transferring anything else. And let me repeat that without all the details. So we get both of our meshes, then we flatten both of our meshes into the same shared space, and then we transfer. And it's a perfect transfer because they're flat in the same shared space. Any imperfection will be because of UV distortion. But in this example, our meshes are so simple that there isn't any to worry about. And in our real head, there will be, but that's why we spent the last video talking about how to reduce UV distortion. So what we have from all of this is a robust transfer environment. We have kind of a universal environment because UV space is the same for everything. And it could have been something else. It didn't have to be 0 to 1 XY. We could have made it any other arbitrary thing. But this is the most convenient because having those UVs is useful for other stuff too. Another quick note is you can see I'm getting this error on this modifier. No group can only have one geometry input. And that's because it doesn't like my wrap mesh via UV group because it's got geometry and target as geometry. So when you're using a node group as a modifier, you have to have a geometry at the top, and it will assume that geometry socket is where to send in the mesh of the object it's on. It will give you this error if you have other geometry inputs and there's nowhere on here to use them. But this doesn't actually stop anything from working, it just complains at you. So since I designed this group to be used as both a modifier, but we'll use it more as a group within other node trees, that's why we have that, but that's also why I am ignoring it. Now, our torus has one more step on its journey, which is restore shape, which is actually our displace that we learned about before. So this is displace from offset, which is the same displace group we've already looked at, but I've wrapped it in a new group with the get offset on Y. So this is designed just for restoring the shape if it has been flattened on Y-axis. And we can see here it's defaulting to position base as the original position, because that's the default output of the save position group we made, and it won't work if we don't have that. And the only thing it's really doing that's different from the setup we looked at before is I put in this vector rotate node, which would be for if we needed to flatten something on an axis other than Y, if our orientation was different. But that just shouldn't happen because everything else we've built here is kind of assuming we're going to be working in this Y-facing space. So I kind of put that in there to future-proof it, but we shouldn't actually use it. Okay, so we've learned a lot from this simple example, and the next step will be to apply what we've learned on the real head. But this example is so simple that there's a few things that it won't have shown us because they don't break because it's so simple. So let's look at one more thing real quick that I originally made as the example to use for this, but then I ran into some issues. I decided I didn't want to confuse everybody. So we're looking at the same setup here that we just learned about, but this time we are wrapping a sphere onto another sphere. And instead of having multiple different GeoNodes modifiers for each step, like we had on the torus, this time we have them as groups inside a single modifier, which is the more practical way to use it most of the time. So this is all the same stuff we just learned about. We get the sphere, we save its position instead of using the save its position modifier here. And then we do all the UV canvas stuff. And we flatten it and wrap it to the target. And then we fix the shape with a displacement, and let's get its normals, although they're not really doing anything because it had a pretty good transfer anyway. So same thing we just learned about. But the problem we've got is that our sphere is rather distorted. It was nice and spherical here, and now it's kind of, well, an oval. And the reason for that is because the UV map of this sphere has been stretched, well, it's been compressed into a square to match our UV space, which is actually what its UVs are if we look at them in UV mode. And that's distorting our sphere because this is actually a rectangle if you unwrap it. The seam is back here. So if we wanted our sphere to not be distorted, we would have to fix the UV aspect ratio. We can go into UV edit on the main sphere, and this is a copy of it. And if we scale the UVs, we can see our UV reference change and that our sphere gets fixed. And then it's just a matter of, well, what do these actually need to be at for the sphere to not have any distortion? And that is a difficult question, and there are ways that we can find it out, but mostly we're going to avoid this problem when we get to our actual face we're using. But I wanted you to know it existed because if you try to make a setup like this yourself, then you'll run into this very quickly. So you can manually solve this by, scaling this until they're even squares, which is kind of hard to eyeball, but you could get some sort of reference, or you could check the position of the points. I've looked for like an add-on that will do it, and the various the usual squaring add-ons, they square a whole island, and that's based on the follow active quads command, which if we use it, it does work, but it's using the aspect ratio of whatever the active quad is. So that, it's not changing anything because it has matched the whole island to this. Also, it messes up the triangles at the top. So I would like to find a proper solution to this. We're mostly just going to avoid this issue for this specific video and use case, but this is annoying to deal with overall. So if anybody knows a proper solution, let me know. So we've learned about the ideas in general, but now we need to apply them to the face, which is more complicated, and there's a bunch of issues that come up and things that go wrong. So let's start with a quick overview. So first up, we have our UVs. They're transferred from this copy of the head, which got them from this mesh, this face mask. This should look familiar from the previous video. This head copy has some shape keys to put it into a better transfer position. We only have half the mesh here because the UVs are being done before the mirror modifier, because I wanted these to be applied to the mesh. So we do the transfer once and apply it. There are pros and cons to doing a dynamic transfer, and we'll look at those when we get back to the UV setup. Next, we have a UV reference. This is what we were just learning about. It is the UV unwrap of the head, but not actually this head. We have a second copy here, which is what we're using as the input for various things, because in the end, this head, the real one, is going to transfer normals from some meshes that will have gotten things from this head, and that way we avoid dependency cycles, and it's more convenient for having a different position for this head. So this is actually just the same as the UV source head we were just looking at, but I have a different copy of it in case I wanted to have different changes to it. The third major component of the setup is the normal source for the main face shape. Currently, this is the same mask as we use for UVs, but we have others we'll look at too. This is actively transferring, so any changes we make to it is going to refine the transferred shape, like getting some more loops in there, and of course, subsurf. So this is where we'll have to refine things like getting this cheek shape just right, but we don't need to worry about details like the nose yet. Where we will worry about those details is in part 4 over here, which is wrapping things onto the face. So here is our sphere that we looked at before. And we also have sillier decal examples, like monkey, yes, ooh, or a pyramid. So this is the part where we'll actually make things like our nose and lip detail and eye crevices and whatever. Everything that isn't the main curvature of the face we'll do here, project onto the face, and then transfer both normals and combine the normals, which is what we'll start getting into in the next video. But there's even more we can do with this. This sort of setup is convenient for so many things, like how about some retopology? I haven't really improved this face at all this whole time. So, if I wanted to do some quick retopo, I can just work flat on the UVs, and it's just going to snap straight on. So this is another case of all of this stuff we're learning about in the context of normals, but these are all-purpose tools that are useful for a huge amount of things. Also, quick note, but this retopology mesh is an example of having a mirror modifier. The origin of this mesh is in the middle instead of at the bottom left of our UV grid. So we're using the extra translation offset option we made. And we can do even more with this UV wrapping than just details. Here is a case of we take this topology in UV space, which is just some flat topology with, variable amounts of subsurf, and I've got a bevel set up to add more loops in some places. And this is this wrapped onto the face. So what this does in practice is it gives us a lower detailed version of the same head, although technically it's based on this version, which has the eyes and nose smoothed out. But let's turn that off for a second. So the more points we give this to work with on the initial plane, the more the face's detail it's going to capture. Let's look at what this does to the normals themselves. So if we give the input mesh more vertices, then it's going to capture more detail of the face, but it's still pretty jagged. So we can also give some subsurf after the wrap, which smooths things out, or even use the smooth modifier. And now we're getting like a smooth, clean version of the shape we already had. And since it's being UV wrapped on, if we repose the mesh by any method, it's just going to respond to that automatically with no extra rigging. Let's turn the detail up even more. We're now capturing a lot more of the original shape of the face, which is a good thing if you're happy with your original shape. In the case of this face here, we're not really, but we can see how this is like a simplified but cleaner version. We can go even higher, although it'll start to lag me out a bit. You go too high and it will start picking up some of the things we're trying to get rid of, like this is our subsurf mesh stretching, starting to mess things up. But even here, we can compare it to the original and see that we've basically gotten to like a slightly smooth version of what we started with. But if we turn that quality back down a bit, now we have a more noticeable improvement still. It's like the same shape, but with all of the surface bits smoothed out a little bit. And that's because that's just literally what this mesh is. So this is a great method if your goal is just to take what you've got and clean it up a little bit. It doesn't hold up for doing much heavier stylization, but you don't always need that, especially if you're doing something more realistic than anime. And the other place it works really well is like clothing or props or anything where you have topology issues with your normals. As long as you can make a UV unwrap and project a grid over it, then you can do this method. And with UV transfer, that should usually be possible. We'll talk more about that later, maybe outside this series, but I'm definitely going to be looking into that more. Okay, so that's the overview of everything. Now we're going to go back to the beginning and go through everything again in detail and see what is different from our previous test setups. All right, so back to UVs. We don't need to talk about these too much because we spent so much of the previous video on them. We've got our UV source. We have a head that is optimized for the transfer, in this case with shape keys that I sculpted on it. And then we have the final head. So our UVs will go from here to here to here, or from here to here, but with this in this position, depending on how we want to do the transfer. I have reset the UVs on both of these just so we can see what's going on. On this one, we have our geometry nodes transfer. So that's doing what I just said, here to here, but with this in that position. That's this node group from last video. On this one, I'll just use a data transfer modifier. And we can see that here, everything looks pretty good. And here, it's a little bit wiggly in the middle. And it actually is on this one too, but we have our fix position center group solving that problem for us. So we've spent so much time on UVs because they are the basis of all of our future transfers. We deal with a world space transfer in 3 dimensions only once because they're annoying. And then after that, we do all of our transfers in 2D UV space. So all of the work that it gets done up front. And we've already done most of that in the previous video. So all we need to do now is apply this. And there's shape keys. So the culprit is my shape keys that I use to flatten and smooth the mesh out. So I don't really want to lose them, but I guess I have to delete them. And then I can apply the UV transfer. And then I guess I have to go transfer them back from the mesh copy. Except this is a real hassle because if I want to change the UVs again later, like if I find a problem, then I have to do that every time. So since we don't have to talk about UVs too much, this is a good time to go on a tangent. And instead, let's talk about position keys, which are the exact same as shape keys, but in geometry nodes, and they don't stop you from applying your modifiers. So what exactly is a shape key anyhow? Well, when you make one, you are setting an alternative position for whatever geometry of the mesh you have changed. And you can mix between it being on and off. There's some other stuff you can do with them, but in general, a shape key is a relative offset compared to the basis, which sounds kind of familiar because we've dealt with doing some rigging by transferring the offset between a base and deformed position. So the information in our shape keys is basically an amount to move each vertex away from wherever it was in the base position. So we can make that same thing with geometry nodes because we can save position attributes. And that's why for geometry nodes, I'm calling them position keys instead of shape keys. So here's a node graph, which has a node group for each of the position keys I've made. And if I turn them on, it's the same as my shape keys. But there are no shape keys on the mesh. Instead, we have them under attributes. So how are these made? We have to make them long form, but that's better than transferring them every time. What I did was I copied the head 3 times for the 3 shape keys, and each one has just one of the shape keys enabled, and all the other modifiers are disabled because the attributes will be applied before anything anyhow. And then I made this group on the main head that just gets those positions and saves them as attributes. So what we've got here is we take the position of the shape key target that we've brought in, and we take the position of the current mesh, and we transfer the shape key's position to the current mesh via indices, topology, and we do a subtract. So we're getting just the difference between the current position and the shape key position. So that's the same thing we've already learned about in the context of transferring offsets. And then we output that offset to these attributes I've made. And when you apply the group, it will write to them all, and if these don't exist, it will create them. Once the attributes are saved, we use them in this group. For each key, I have made a group that applies the offset and gives us some options. The basic function of this group is very simple. We're getting a named attribute based on the string name of the attribute key, and we're setting the position as offset, and then they chain into each other. So, extremely simple there. But we need to add a few more options to make it more usable. So here it is with some more features. Position versus offset. We are switching between set position using the input as a position to set the geometry to, and this is offsetting by the inputted attribute position. So this is what we're actually using for all of these, but we have had plenty of situations where we have been setting to instead of adding an offset. And theoretically, we could have saved the full position and then done the offset math here instead. You can really do it in any combination that suits your needs, but this just happens to be how I built it. So we've also got these mix nodes for a mix factor, which lets us turn these on and off. So in the case of an offset, we're mixing between the offset or nothing. And in the case of setting to, it is the attribute or the current position. So that serves our purposes pretty well, unless we want to be able to use it after a mirror modifier. And then we have the problem, which is that the mirror modifier is designed to mirror everything coming in before it, but it's not mirroring the attributes data. In fact, it doesn't mirror any attribute data. It mirrors things that existed before the geometry nodes like vertex groups and UV maps, but it is not mirroring our position keys. So we'll have to mirror ourselves, which is what these nodes do. Problem fixed. So we're looking at the position of the mesh beforehand, looking at the x-axis, everything that is less than 0. And if they're less than 0, then we've got a version of the attribute that has been inverted. And then we have a toggle if to mirror x or not. So that solves the mirroring issue. So why bother building that instead of just putting this before the mirror modifier? Well, the whole point of these position keys is it gives us a lot more flexibility than the regular shape key system. Regular shape keys always happen to the mesh before any modifier. And once they're on, you lose access to all previous states of the mesh. As far as the modifier stack is concerned, whatever the output of your shape keys is at any given point, that's what the mesh is. You can't access the basis and then have, say, a node group that uses one key and a different node group that uses another key. Whereas with our position key system, we have our original position and whatever keys we need and any amount we need in whatever groups we need. And in the case of these normals here, this is fine. I'm just replacing my shape keys so I can apply things. But this is just hugely powerful for other geometry nodes setups. So I suspect in the future, we'll be using a lot more position keys for lots of things, and hopefully we'll get an operator that applies all existing shape keys as attributes at some point. It wouldn't be too hard to make. But until then, it's a bit of a pain to set them up, but it's not any more effort to make a position key than it was to make a shape key in the first place. It's annoying if you have to transfer a bunch over, but in the future, you can just work directly with position keys. Now, the catch is that the performance is a bit worse than shape keys, because with shape keys, once they're on, it's not constantly recalculating them, whatever the modifier stack runs. But for position keys, it is. But they're still pretty fast. Like, this whole tree, 1 millisecond, about a third of a millisecond per key. You could do a whole character expression system and the performance would still be fine. Well, that was a fun tangent, but now let's get back to our UV map. So I had applied the UVs, and we should head over to UV edit and just double check them, and they're not there. In fact, there is no UV face because it's down here. It's an attribute right now, not a UV map. And we want it to be a proper UV map, not an attribute, because that affects what, like, nodes access it in shaders and some other stuff. So we're just going to hit convert attribute and UV map. And now it's over here where it belongs. And it still looks fine. And we can look at it in UV space. If we hadn't done our center line fix in the nodes, we could now come in here and fix it. But it's already done, so looking good. A manual edit I have done is taking everything from the back of the head and sticking it outside the UV grid. So here's our mask. If we invert that, then these were all messed up from the transfer. So I just hit an unwrap. I'm going to flip them 180, scale them down 0.1, and just stick them off over here. The only other thing left to talk about on the UV front is how to model this clean mask to get the nice UVs in the first place. I've had some questions about how to do this with very even loop spacing. So I will show how to do that, but it's pretty dry and not everyone is going to need to see that. So I'm going to stick it at the end of the video. Next topic, we are on to the UV reference. So this is pretty familiar. Not a whole lot has changed here, but I have added some features over the simpler example. I have made a switch to control if we do the Z flattening, which doesn't matter here because our UV map already doesn't have any Z, so that's disabled. And we've got a switch for the center line position, also disabled in this case because we've already fixed it in this UV map. And I have put the split edges inside a group. We do actually need the split edges in this case because we need to split our head's UV islands. If I turn them off, we're left with faces connecting those points. So We knew why we needed it, but why is it in a group now? This is actually just a small performance optimization. Take a look at how long this group takes to run, 7.5 seconds. If I turn it off, then obviously it's not running, so it doesn't take any seconds. 8.8 seconds. The incoming is just a single value. It's either 0 or 1. We could put like a vertex group here if we needed to. So what this group is doing is it's putting that same selection into the split edges node, but also it's checking a attribute statistic. Here's why. Let's plug in just these split edges, and outside the group, we'll toggle it on and off. So currently it's splitting all edges in 23 ms, and now it's splitting none of them in 9.9. So, it varies a little bit. Now let's put this back on, and now it's doing the same thing for everything, or none in much less, like fractions instead of 9. So what's going on here is this node is checking if any of the incoming selection is more than 0. This is the max output on attribute statistic. So if any attribute is greater than 0, it's going to be true. So this is simply checking to see if there's actually any edge splitting taking place. And if it's just 0, then it doesn't run the split edges node, because the split edges node takes some time to run, even if it's not actually going to split any edges, even if the mask is 0. So basically this is saving us like 15 to 20 some milliseconds, which probably doesn't matter, but it was an interesting thing I noticed. And I'm not sure if that can be fixed or this functionality can be built into split edges, but I decided to build this group for the hell of it, and I decided to tell you about it because you should be on the watch for performance things like this in geometry nodes in general. And often you can save a bunch of performance by using a switch like this, and that could add up in complex setups. Okay, and I don't think I added anything else since the previous example, so that's it for our UV Flatten group. And over in our UV Canvas group, nothing has changed here either, our canvas transform. Also, if I disable these, there's not actually anything inside this object because this is literally just a visual reference, but I do have a 1x1 plane here, so we can just check our canvas bounds. But yeah, on to the next. Moving right along, here is our face mask that we're using as a normal source. Its geometry nodes is one of those offset transfer rigging methods we looked at. In this case, it's one of the simpler ones because we don't have to worry about restoring volume or anything like that. So it is copying transforms that happen on this mesh, even horrible ones, but it does need the undeformed position to be saved on the target mesh. We also have a bunch of other modifiers that actually change the geometry to get some nicer normals out of it. We're not really going to go into those in this video. We're building this whole setup so that we can get to the point of talking about like what source actually gives us the normals we want and how do we get it clean, which is, where I wish I could have started this series, but we have to build the setup to allow us to have that conversation. And the mask doesn't need anything fancy on the UV side because it already has a UV map that will just lay it flat. So we don't have to do anything with nodes to get that. Next up is our alternative normal source, which is this topology wrapped onto the face to make this. And there's nothing fancy here. It's just a grid that has some modifiers on it. It has a UV map already. It doesn't need anything fancy. The mask made out of it does have some geometry nodes, and again, these should look familiar. We've got a couple instances of our UV Flatten node, which has received some new features, but we already went over those. So this is just reusing the same things we've already built. So it does have some slightly different settings on some of these. And note that, of course, some of the settings are on the modifier version and some are on the node, and we could plug some of these into inputs if we need them. My general policy is to make more inputs as I go. So as we get into more complex things in future videos, who knows what we'll do here. And we may end up having to restructure all of this, but Yeah, I don't know where we'll end up, but this is already a lot more efficient and a lot cleaner than my previous test setup from way back in the first video, I can tell you that. Next up, we have our sphere decal, which is the same as when we looked at it before. There have been some changes to the get normals group, but we'll talk about that when we get to the normal transfer. The rest of this is the same. And our other crazy decals example is exactly the same as well. And basically all decals will just use these exact settings. It's very nice and straightforward. It's the same group, wrap decal to face. And for that retopology example, it is the same group again, except using some of that extra translation. So some different setting here, but the nodes are unchanged in here. Also, I've got a bit of displace on it after, just so we can see it a bit better. The last place we have some big changes is in our normal transfer group on the main head, where we actually bring on our normal source and do the most important part. This is mostly the same as what we've had in previous videos. We bring in the vertex group to mask to the face. We have to switch it to face domain and use this to have it mask out everything in the faces that we want, which is those. And then we capture the original normals so that we can mask to them, and also so that we can do a mix fact to them. And what's new is that we are now using a store attribute node instead of an output property, because I just want to always use GN normals. That is, of course, just a preference. It could be either way. We could still output the normals here. And the other big change is down here in that get normals group. So down here is where we are getting the normal source. We're using this group that lets us choose between object or geometry. I've hidden relative. In this case, we're using this as a modifier, so it's an object. But in a final setup, we might build this entire stack instead of as separate things with modifiers on themselves. It might be all one big node tree or something like that. So that's why, again, I built these groups to support both use cases. So over here in get normals, we input the source geometry, and we tell it what UV maps to use for the source and destination, because it's going to unwrap them both into their flat UV position and then do the transfer there. And we've got a bunch of output options. We can take a look. That's just passing the geometry through. And here is the normal source unwrapped to its UVs, which, well, there you go. So this group is one of our heavy lifters, so it's gotten even more complicated inside, because this group has to handle our UV space transform, or really whatever other position we plug in. So it's doing a bunch of input checks. If there's no source position, use the current mesh position. If there's no destination position, use the current mesh position. And you can put in a custom index order if you want, if you're using the index transfer. And we have outputs for multiple types of transfer. So we get our source mesh, we save its position, we capture its normals to point, then we flatten it with our UV flatten group, which we have looked at before already, another reuse group. And then we use that for the transfer. And we also restore the position and re-output it. And that is so that we can keep that normal captured on it. And we also output a second version in the transfer position, and this is just for debugging purposes so that we can see what's going on, or I guess if you wanted to transfer something else in this position conveniently. Now, the place that gets confusing is source position versus destination position, and then on the transfer node, we have source position. But what's going into source position? If we look past all this other stuff, it's actually destination position. So this is the thing you have to remember, that source position is currently mislabeled. We've talked about this in previous videos, but I'm going to go over it again because this is confusing. And also, by the time you're watching this, they may have fixed this, or they may have changed it to something totally different. So on the transfer attribute node, source used to be named target. And that didn't make much sense because you think the target of a transfer is the mesh that the data is going to, but this is the mesh the data is coming from. So they removed that confusion by changing it from target to source in 3.1, I think, but they didn't change source position, which is now even more confusing because this is not the position of the source, it's the position of the destination. Well, what I've been calling the destination. Because remember, the order of operations for this node is, say you're like setting position or something. What it's going to do is when it evaluates set position, it says, okay, we're setting this geometry based on this position input. So where does that come from? It comes from a transfer node. Okay, go get it from the source. And this socket is saying, what position is this geometry in? So hopefully they fix this. I've been using the terminology source for source and destination. So you just have to remember this source position is actually the destination position. So that's why that's plugged into there instead of that being plugged into there. And as long as you keep that in mind, all of that should make sense. The other thing I've done is pulled out the split source edges, which I'm not using in this case, but we could. So that's because before this was just a set position, but I replaced it with a UV flatten so that we would have some more options, like if to split or not. I'm only using the split so far, not flatten Z or fix X centerline or mask. These could come up later, in which case I'll deal with them later. But for now, they're not necessary. Usually, you could just put the fix X centerline before this or whatever. Having some redundant things like that is pretty bad when you're working with shader nodes and it has to deal with compiling all the nodes, and even things that won't be used and have zero FAC can mess up your compile times. But in geometry nodes, it's just not that big a deal to have some redundant bits like that. All right, so I think that has covered everything that has changed from our example setup to the real setup. I might have changed a few labels and outputted some things and some other stuff, but that's all the broad strokes. And I may change more by the next video, but if I do, I will tell you or it will be obvious. This is the broad skeleton of our normals canvas setup. So now we can start doing things with it. Okay, we're done with the main topics of the video, but I'm going to throw in a segment here on how I modeled this UV transfer mask, because some people were having trouble getting good results. So if you know how to make this sort of thing, you can stop here. Don't forget, like, subscribe, Patreon, and all that. And if you want to know, keep watching. So our goal with this mask is to get good transfer, and that means evenly spaced loops for an evenly spaced UV map, and for it to line up with key parts of the mesh. So I'm basically modeling this like what the face would be if it didn't have detail on it. This bottom loop lines up with the bottom of my jaw section. This loop lines up with the jaw line. And then everything else is basically just an evenly spaced curve. And that's true in this direction as well. Now the shape is not actually mathematically perfect by any means. I did model this by hand. You can see some issues there that I should probably fix. I am looking into ways to make like a mathematically perfect version of this, or like a really convenient one with probably Bezier curve lofting, or some sort of surface wrapping. There's a bunch of things I'm looking at, but for now this is good enough. The basic process we're going to use is to make some reference curves to get the main shapes. Then we will hand model a mesh using those reference curves, and then we will use the loop tools add-on to get even spacing on it. I'm going to do some combination of like skipping and time-lapsing through this, because you just need to get the general idea. So first of all, a Bezier curve for the main curve of the face. We can give that a little bit of bevel to make it a bit easier to see it. So that's about right. I'm not going to put in as much time refining this as I did for the real thing, so this is just a rough process. I've marked a separate material on the parts of the head I'm not using. We want this mesh to always be slightly inside. all the way around. And it's actually a bit outside on some of the draw parts, but that doesn't really matter. Okay, so that's Bezier curve 1 working pretty well. Now I've duplicated that, and I'm making a second one to be the jawline. And the other one I'm making is a brow line. Okay, so now filling in between these is a much easier task than just modeling the whole thing out of nowhere. Let's get one more for this angle, because that one can be a bit tough to figure out. And I'm sure someone will come along and tell me a better way to do this, and they're absolutely welcome to, because that's something I've been thinking about, but I just haven't had the time to really get into it. All right, so there's my reference curves, and I've chucked them in their own collection. Now I've made a plain origin point, same as the head, and I've got snapping on, and let's start snapping this on to about the right places. And going all the way down there can make it confusing, so you can kind of take this in whatever slices you are comfortable with. And now, loop cut, flatten that out, line it up with the reference. This doesn't have to be exact yet. It has to be mostly right. Keep in mind, our goal is 10 by 10 once mirrored. So 1, 2, 3, 1, 2, 1, 2, 3, 4, 5. So that's what I'm replicating. Again, shrinking flatten with Alt-S should do the job for the most part. And it's not a big deal if we mess up the loops in the middle right now, if their spacing is messed up. The important thing is getting these boundaries in. So I'm going in and out of snapping, and I'm also just moving things around freely. It can help to bring it out a bit more than the face so you can see what you're doing better. It's always easier to smooth it in than to bring it out. The center line is nice and easy to do. And if you have like shape keys on the face, like to hide the nose or something, then that can also make your life a lot easier. So that's getting there. I should just snap this to the curve at this point, really. And easy to quickly fix the center line with snapping to 0 based on the 3D cursor, which I have in the middle. All right, so now that's pretty roughed in. I'm going to repeat that process for these other panels. Okay, so I've now done that for all of the parts except for under the jaw, which we'll deal with last. So it's mostly correct, but there's a lot of bits that are uneven, especially if we compare to the original. So now we are going to get those to be more even. Blender comes with an add-on called Loop Tools, so go enable it if you don't have it enabled already. And it shows up under the edit menu here, and it has several commands that will make our lives very easy. We're looking at space, relax, and flatten. So what do these do? Space command, you select a loop, or edges, better edges usually, and you hit space, and it evenly spaces them out. Now, if you select like this, then it's selecting the vertical edges too, and then it's going to go nuts. So you have to do horizontal edges, either by doing it in edge select mode or on space. There is an option here for parallel. So now if you select just one and run it, it does the whole mesh for all parallel edges. I generally prefer to control the selection. Now, relax works in a similar way. It works on one edge. It relaxes it. This does cost us some volume. So if you're using relax, you may have to adjust the iterations or be prepared to fatten it out a bit. So we'll use that very sparingly. Mostly it's space and flatten we care about. Flatten finds a plane to flatten it onto. So that's pretty nice for most of these. But we have to watch out for it messing up our curvature. We look at this, it's kind of going up. We kind of want it to be flat across. And the easiest way to fix that is actually to mirror the mesh at this point. So I'm going to check that my center line is on 0 by scaling it to the 3D cursor, which is still at 0. And then mirror modifier. And just immediately apply that. And now when we use flatten, it's going to give us better behavior. And that is actually what the mesh symmetrize command does, by the way. It's the same thing as deleting half your mesh, adding a mirror modifier, and applying it. Let's not lose track of our reference curves either. So I can just hit the whole thing vertically with space, but that's actually making things kind of uneven. It's not ideal. So I only want to hit up to the up to this point where that reference is with space. That's a bit cleaner. And then I'll also hit everything above it with space. But I want to make sure I maintain that line. We can also hide the model to see what we're doing a bit better. So right now I've got more curvature here than here, which is why I have this reference. So this is a good time for some relaxing. Do that up there too. I'm going to avoid relaxing these top loops, I guess. They could use it. So now it's just a matter of pushing and pulling some points around and hitting things with space and relax and flatten. And doing that over and over again is basically going to slowly smooth out this whole mesh. So you do kind of spot fixes, you keep an eye on your references, you keep doing this. And after a bit, you will have a suitable face mask. So now I'm going to move forward to the UV part. Oh wait, I nearly forgot the underdraw part. So I'm leaving that until everything else is pretty clean. And now I'm going to delete half the mesh again, because we're going to work with this mirrored. And this part I left like this because it's pretty easy. I'm just going to go to vertex and snap these to the appropriate areas. And maybe it can stay on face. That just depends on your mesh and preferences. So get those all in the right place. Maybe back them off a little bit from the edge. Pop them off a bit with Shrinkwrap. That's how I ended up with a gap on mine earlier. I was doing too much of this. Hit that with some of the space command. And basically, we left this because this is actually longer than these segments, but we don't care because it's just filling in under the jaw. It doesn't have to be as clean as the rest of the face. Okay, time for UVs. UV edit mode. This is what it started with, so we're going to have to hit it with a fresh unwrap, which has given us mostly the right shape, but it's kind of distorted. It's not hard to get this into the right shape. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good, I didn't mess up the aspect ratio. So now we can use something like text tools and its rectify or square UV squares. And all of these, of course, are variants of the follow active quads command, which is why that didn't do anything, because it's doing the same thing. So the important thing here is that we want to fill our UV space evenly. I'm going to cheat a bit here by doing constrain to image bounds, and that just slides over there and down and up. This one we want to make sure is at 0.5 on X. So if you type that in there, it'll set the whole thing. Then, that's at 1, that is at 1Y, etc. And now we just want these evenly spaced. We have 10 of them, so every 0.1. And there are tools that can do this in various ways, like Text Tools has that. That'll do it. And we can double check that they're in the right place on Y. Yep. Or you can just come here and select a whole loop and type it. It's already at 0.9. I guess we need to be doing X. So that should be 0.6 and 0.7. This is one of those things where I'm sure there must be a better UV tool for this. If it was a more complicated mesh, I would just unwrap it as a mesh and do this with mesh tools, but, that still only took like a minute. And render, there it is. Oh. Perfect, clean UV map. All right, that's it. I've just about lost my voice, so good thing this is the end. Thank you everybody for watching, and as usual, like and subscribe, leave questions, support me on Patreon if you like this sort of thing, and I'll see you next video.